Hi, I'm Dalton, and this is Physics 2212's Lab 4, Dealing with Circuits. So a quick introduction. The purpose of this lab was to use the CCK circuit builder to build circuits and observe their properties. Some of the main things we're doing are observing resistors in series and parallel, measuring current and potential differences across circuits, and observing the behavior of resistors and capacitors. So the principles used. We use the node rule, which pretty much just tells us that current in and current out of a point are going to be the same. The loop rule, which is that the potential difference of a round trip, or in other words, like all the way around the circuit, will be 0. And then a few basic formulas like V equals IR, are formulas for resistors in series and parallel, and the capacitance formula. Quick preview of the results. I got the RC value of 5.988 seconds, and came to the general conclusion that higher resistance in a circuit means a longer time to charge the capacitor and a longer time for discharging. So here's part 1 of the experiment. We just have a simple circuit set up with an EMF of 3 volts, a total resistance of 147 ohms with 2 resistors in series, as seen over here. And then using the V equals IR formula, I predict that I, or the current, would be 0.02041 amps, and as seen in the image, it's 0.02, which is pretty much the same. And just looking at it, if we were to switch the orientation of the ammeters, at least in this program, we would get the same result. So part 2 of the experiment. The resistance of the voltmeter made it so that the current through the circuit is 0, because we treat voltmeters as if they have like an infinite resistance. But we can still see that the EMF is 3 volts, as shown by the voltmeter on the image. Part 3 of the experiment. We looked at the potential difference among points around the circuit. So we have A to B is 3 volts, B to C 0, C to D negative 0.96, D to E 0 again, E to F negative 0.204, F to G 0, 0, 0 until the end. And overall, if we total all this up, we do get 0, which makes sense considering our loop rule we talked about earlier. So here's just a quick graph of that. We start from A, going back all the way to H at the end. And if we look at, we start at 0 and end at 0. So if we were to go back from H to A, there's no change, which is also what we're looking for according to that loop rule. So here's part 4 of the experiment. And what we did here was take the same circuit and take one of the ammeters and put it branched off in parallel with one of the resistors. So when you put that ammeter in parallel, all the current flows through the ammeter that has no resistance and avoids the resistor. So calculating based on this, we do V equals IR again, with R is only 47 ohms, and get 0.06 as our current. And this is the same as what is being read on the picture to the left. And then we had to do a couple of basic resistance calculations. For the 47 ohm resistor, manually calculating, I got 48 ohms, and for the 100 ohm, I got 102, which is pretty close. And then for the wire and ammeter, both 0 ohms. So here's part 5 of the experiment. We observe the charge of a light bulb as a capacitor is charging up until that capacitor is fully charged, at which point the current's going to stop and just stay there. And then when we remove the battery, it's going to cause the capacitor to discharge, and the bulb will remain on until the capacitor loses its charge and goes back to normal. So we had to time this. For the 10 ohm charge to get charged, I got 5.6 and 6 seconds to discharge. 20 ohms, I got 10.1 seconds to charge and 12.3 to discharge. So here's a continuation of part 5. I ended up graphing the voltage versus time graph for a 30 ohm bulb, and getting the result of that, we got a line of best fit with a slope of negative 1.67. From this, we can do 1 over that slope to get the estimated RC, which I got to the 0.5988, as we talked about in the preview. And theoretically, this value should have been 6, which is really close to the same, and it's probably just due to small estimation errors that cause that difference. So some potential error could just be incorrect recording of time, possible calculation errors, and errors in the circuit program, just simple stuff. So here's the first what if. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated one? What would be different about this? So the ammeter used in this lab was said to have a resistance of exactly 0, while in real life it would not be 0, so there's going to be added resistance from that, which we would have to account for. Another what if question. So if you were doing this in real life and used a real battery to charge the capacitor with no resistor, how quickly would our ideal model predict the capacitor to charge? So essentially, in real life, the capacitor would charge a little slower than in the model, and this is again due to the resistance of extra things. So like the ammeter, which we talked about, the wire would have some resistance, and even the capacitor. So in the model, all of that resistance was negligible, so therefore the capacitor charged a good bit quicker than it would have in real life. But that wraps it up here, so thank you, and that's all.